Hey, let's look at some of these AP Live calculus problems from the AP Live videos. Just created a cumulative worksheet that hit upon topics that would be good for AP review. So number one, use continuity conditions to answer and justify below questions. So we have a piecewise function here. We have a cosine graph that's to the left of 0. And then we have a different graph, x squared plus 1, that is defined at 0 and also to the right of 0. Is the function continuous at 0? So we're going to go through our continuity conditions, and just to refresh our memory, the first is, does the point exist at C? So if we're trying to decide what our C value is and you're looking at a piecewise function, just look at the restriction. Whatever value is here, that's going to be your C value. That's going to be the center of attention in terms of where our continuity is in question. The second condition is, does a limit exist? That means, are the two graphs moving towards the same y value as we approach a certain x value? So sometimes we can rely on one statement. Other times, like in this example, we're going to have to rely on two statements because we have two different graphs defined on either side of C, of 0 rather, and we have to look at the movement from both sides. And if the limit exists, then we go on to the third condition. And if our point and our limit are in agreement with each other, then all three conditions pass. Our function is continuous through that point. So does the point exist? F of 0. F of 0 is defined for the second piecewise, so 0 squared plus 1 is 1. Second condition, does the limit exist? So we're going to look at the limit from 0 from the left side of 0, as well as limit from the other side of 0. So limit as x approaches 0 from the left side of 0, we use the first piecewise, so cosine of 0 is 1. As we evaluate the limit from the other side of 0, we use the second piecewise function. The one side limit is just there for notation, but in actuality, we're just going to plug in that whole number 0. We're not going to play with decimals. So 0 squared plus 1 is also 1. So the limit exists, and our second condition passes. Now the third condition, we look at the result of the first condition and the result of the second condition and see if they are in agreement. Yes, the point is defined at y value of 1, and the limit, the graph, is approaching the same y value as where the point exists. So all three conditions pass. By continuity conditions, our function is continuous at x equals 0. All right, number two, again, we have a piecewise function, and we're going to step through our continuity conditions like how we outlined in example 1, in problem 1. And here, the distinction, though, is that our C value is 1, okay? But the distinction is that it's not two different connected parts of graph looking to see if they are going to be moving towards the same y value. We have a connected part of graph all contained within this first piecewise, because when it says for x does not equal to 1, that means for all values except at 1. So to the left of 1 is this function, to the right of 1 is this function, and the only time that it's a different definition is at 1. So that's for that's just an order pair, as opposed to here where we have two connected parts of graph. Here we have a connected part of graph on either side of 1, and then here that's just a point. So if we step through our conditions here, does the point exist? We know our C value is at 1, so f of 1 is equal to k. So that's still inconclusive. We were trying to look for k, so that doesn't help us just with that statement alone. So our second condition is, does the limit exist? Now, we don't have to rely on two one-sided limits because we have the same function on the left side of 1, and we also have the same function defined for the right side of 1. So we can just rely on one limit statement because as we approach 1 from both sides, it's the same function. So we set up our limit statement, we plug 1 in, we get 0 over 0, so that tells us that the limit exists, but it's hiding from us right now because there is a hole that's getting in the way. So we're going to go through conjugate method to see if we can identify that common factor, reduce, reevaluate, and see if we can get down to that limit. So when we multiply by the conjugate, we copy down the exact same expression as we see here. The only thing we changed is that sign in between, so that minus will become plus. Whatever we have here, we're going to copy the same term down below, and now we're going to FOIL. So if we expand this out, we get x plus 3. Middle terms goes away, minus parentheses 3x plus 1. Denominator, you're going to leave as factor form. We're not going to try to expand this out at all, because this x minus 1 is eventually what we want to cancel out. So we don't want to get muddled through this expression. We want to leave it separated so it's easy to eliminate. Now, the parentheses protects the 3x plus 1. We can distribute that negative through, and we get x plus 3 minus 3x minus 1. Combined like terms, we get negative 2x plus 2. We can factor a negative 2 out, and then we can see the x minus 1 is a common factor. We can eliminate. Now we can reevaluate. Now the hole that was causing 0 over 0 has been removed. We plug 1 in for the remaining x's, and we get root 4 plus root 4, which is 2 plus 2, which is 4. Negative 2 over 4 is negative 1/2. So all this is to show us that the limit does exist at negative 1/2, or limit exists and limit is equal to negative 1/2. And now we're going to compare our first two conditions here. If we want the function to be continuous, then f of 1 has to be equal to the limit as x approaches 1. And if we want that to be true, then k must be equal to negative 1/2. So we know k must be equal to negative 1/2. All right, number 3, we have a function that's defined as g of f of x. So we have a function f within the g of x function. We want to find h prime of 2. Before we can find h prime of 2, we first have to find h prime of x. And to find h prime of x, notice that there's a function within a function. And here is just a reminder of what the chain rule is. So chain rule says take the outside function's derivative and multiply by the inside function's derivative. So here, I'm going to rewrite my my full expression for h of x, which is g of f of x. So we're going to go through and step through our multiple derivatives here. Our outside derivative is g prime of f of x multiplied by the inside function's derivative, which is f prime of x. And piece by piece, we're going to see if we can get this out of function notation. So we're going to find h prime of 2. So first thing, let's replace every x with 2. So when we do that, we see that this is still a messy expression. We can't do all this at once, so let's start with the part that we can figure out. Let's find f of 2. So f of 2, okay, so our f function is going to be the one I'm going to highlight here. Okay, so we have our f function, f of 2, so f of 2 is going to be 3, so we can replace f of 2 with 3. So now we have an easier path towards our answer here. G prime of 3 is asking for the slope of the g graph at 3. So here's my g graph. The slope of the g graph at 3, we want to find the slope of this line, so if I pick 2 points that are easy to identify, and I just find the slope, I go rise up 2 over 3, so my slope is 2/3. And then a separate part that I need is f prime of 2. So at 2 on the f graph, I need to figure out the slope of this line segment. So if I pick 2 points that are easy to find here, I go down 1 over 1. My slope is negative 1. So I have 2/3 from g prime of 3. I have negative 1 from f prime of 2. 2/3 times negative 1 is negative 2 over 3. All right, number 4, h prime of 1, given h of x, find h prime of 1. So we look at how h of x is defined. It's defined as the numerator over denominator. This is going to be quotient rule. So f prime g minus f g prime all over g squared. So now my f is defined as my numerator. My g I'm going to assign to be the denominator. So f prime is the derivative of the numerator, so k prime of x, times the denominator, 3x, minus the numerator, k of x, times the denominator's derivative, 3x becomes 3, all over denominator squared. Okay, so my denominator squared, I'm going to get 9x, or 3 times 1 squared. Replace every x with 1. So k prime of 1, k of 1, and 3 times 1 quantity squared. K prime of 1, we look at our table here. So k prime of 1 is going to be -5. K of 1 is going to be 2. So -15 minus 6 all over 9, we get -21 over 9, which reduces to be -7 over 3. Number 5, we're asked to find the derivative. This is a problem that is chain rule, but there is a nested portion. It's not just outside and inside. There's an outside, there's an inside, and there's an innermost function. So if I want to spell out the different parts of chain rule, I can maybe use this as a notation to indicate what I'm doing. There's an outside, inside, and inner function. So I'm going to take turns with each of the derivatives. First, I'm going to take the outermost function's derivative, f prime of g of h of x, times g prime of h of x, times the innermost function, the h prime. So the first thing that I want to do is I want to rewrite this expression to make it easier for me to see all the different parts. So that squared, I'm going to push that out as bracket squared. So now it makes it easier for me to see that anything with a bracket and exponent outside is going to represent my outermost function. Directly inside the bracket is the tangent of the parentheses, so I'm going to notate that as my inside function. And then the inside, what's inside the parentheses, is going to be the innermost function. So we have 3 different layers. We're going to take turns with each of their derivatives. So the first is bracket squared. We can think of the bracket as a variable. The derivative of bracket squared is 2 bracket to the first power, so or 2x squared, or 2 parentheses squared, 2 parentheses to the first power rather. Tangent's derivative is secant squared, or parentheses. And then the innermost function, 3x squared, becomes 6x. So we do power rule for the first, trig rule for the second, power rule for the third. And then we fill the bracket in with what it came from, no changes. We fill the parentheses with what was initially inside, no changes. So now we have the derivative. I can do a little bit of cleanup. I can push the coefficient all together in the same location. So 6x times 2 is 12x. Tangent 3x squared, secant squared 3x squared. All right, number 6, given that p of x equals the cube root of 2x minus 1, find the derivative of an inverse at 5. Now, let's establish a couple of things here. First is that a function and its inverse have a couple of points of relationship here. One is that they have something called corresponding points, or what I like to refer as corresponding points. That means if the original function has order pair 1, 2, then the inverse function must have order pair 2, 1. If the original function has 3, 4, then the inverse function must have 4, 3. So at their corresponding points, they have particular relationship, numeric relationship with their slope of their tangent lines. Their slopes at their tangent lines at the corresponding points will be reciprocals of each other. So if 1/3 is a slope of a graph at a point, then 3/1 is going to be the slope of the inverse at the other point. So first thing I'm going to do is I'm going to try to find these corresponding points. We know 5 is going to be the x value of the inverse, which means that 5 must be the y value of the original function, right? So I'm going to set my p of x equal to 5 because I know that's my y value. I'm going to try to work backwards to solve for x. Cube root of 2x minus 1 is equal to 5. I'm going to cube both sides to get rid of that cube root. I get 2x minus 1 equals 5 cubed. 5 cubed is 125. Add 1 to both sides, divide by 2, I get x equals 63. So my order pair for my inverse function is 5, 63, which means that my original p of x must have an order pair that's 63, 5. So now I can move towards what I want to do, because from p of 63 I can find the derivative of p of x, plug 63 in, find the slope, and then use that slope to turn around and figure out what the slope of the inverse is at its corresponding point. So back to p of x, I'm going to find the derivative going through chain rule, bring down the 1/3, subtract 1 from the exponent, multiply by the inside function's derivative, clean this up, plug in 63 in for all the x's, and we get 2 times 63 minus 1, and the cube root of that will take me down to 5. 5 squared is 25. And then I have 2 over 75. That's my slope of my p-graph. So if I know the slope of my p-graph, then I know the slope of the inverse at its corresponding point, which must be the reciprocal of 2 over 75, which is 75 over 2. All right, number 7, we have an equation, and we're asked to find the second derivative. We're going to have to step through implicit differentiation because we have y involved, and we also have to find the second derivative. So we're going to go through implicit first. Y squared's derivative is 2y dy dx. 3x becomes negative 3, 7 goes 0. Let's solve for dy dx first. So add 3 to both sides, divide by 2y. So I have my first derivative. I have to go through this one more time to get to my second derivative. So I'm going to set up this ready for my power rule for my next derivative down. So I'm going to rewrite that 3 over 2y as 3 halves y to the negative 1. Let's go through power rule again. Bring the negative 1 down, subtract 1 from the exponent, so negative 3 halves y to negative 2. Now I just took y's derivative again, so it's going to produce another set of dy dx. Clean up this expression down in front. I get negative 3 over 2y squared. Now we want to express our second derivative in terms of just x and y, so I want to replace that dy dx. Well, we know from our first derivative dy dx is 3 over 2y, so I'm going to take this 3 over 2y, put it in for my dy dx, and that way I can combine my expression. So negative 3 over 2y squared times 3 over 2y cleans up to be negative 9 over 4y cubed.